Circles, let's go. Here are some terms you better know about circles. Diameter, segment going all the way through the circle's center from edge to edge. Radius, a segment from the center to the edge. By that edge length, we're referring to the circumference, the full length all the way around. Some less familiar terms include chord. A chord is a line segment whose endpoints are on the circle's circumference. So actually, there are a number of chords in this picture besides just that blue one. The purple segment, known as a diameter, is also a chord because where are the endpoints of a diameter? You guessed it, on the circumference. So a diameter is a chord, but not all chords are diameters. In fact, a diameter is the longest chord in a circle. Less familiar terms also include secant and tangent. So a secant and a tangent both refer to lines. You'll notice the other ones are line segments. A secant line crosses a circle twice. So you can imagine a secant being an extended version of a chord. So take a chord and extend it into a secant line. So if a secant crosses a circle twice, you'll notice a tangent crosses a circle only once. It just barely grazes the surface of a circle, the edge of a circle. And we call that location the point of tangency, where the circle and the line have that commonality. We've seen sectors before. A sector is a slice of a circle, like a slice of pizza, a section of the area of a circle. An arc, I want to mention with specific emphasis here because we'll talk a lot about arcs as well as chords. Chords, again, a segment, a line segment with endpoints on the circle. An arc is a section of the circumference, a portion of the circumference of a circle. So we're going to talk about the length of arcs as well as the measure of arcs in just a moment. Segments aren't as important for our study now, but keep in mind a segment is sort of the part of a circle sectioned off by a chord. You can kind of see it as being a strange slice, not the way you'd have pizza, but maybe the way you'd have a cracker or something. So chord and arc I want you to focus on here in terms of unfamiliar terms. First term review. We've seen two formulas when it comes to circles before. Those formulas are circumference and area. Suppose a circle has an area of 36 pi square centimeters. What is the exact circumference? So exact circumference means we're going to be leaving pi in our answer. That's what exact means. Don't use any kind of strange exotic decimal approximations. Just use pi. Okay, this formula requires the radius, which we don't have. What we do have is the area. The area is 36 pi square centimeters. Well, the area formula is pi times radius squared. So by equating these two, I can find that missing radius, which solves the problem. So divide both sides by pi. This will leave us with 36 equals r squared. Take the square root of both sides, and you'll find that the radius is 6 centimeters. So if the radius is 6, we now have the radius to plug in over here. So that gives us 2 pi times the radius, which is 12 pi. And this is in centimeters. And this is a circumference, so this will stay in centimeters. Conversely, a circle has a circumference of 11 pi inches. What is the exact area? So area requires radius as well. Are we given radius? No, we're not. We're given the circumference again. No problem. Circumference is 11 pi, but the formula for circumference, you'll remember, is 2 pi times the radius. So just like before, in order to find the area, we need r. So let's find r. Divide both sides by pi, leaving us with 11 equals 2r. Divide both sides by 2, and hey, r is 5.5. Pretty easy. So now we plug in that radius that we have just found. So in this case, that would be pi times 5.5 squared. Once again, exact area, leave pi as part of your answer. So I'm just going to focus on the numerical portion. 5.5 squared gives me 30.25 pi. And this is area, so it'll be square, in this case, inches. We mentioned arcs earlier. Arcs can be thought of in two different ways, both the length and the measure. The length of an arc is what you'd think it would be, the actual physical length of the arc. How many units is it? How far is it from one point to the other along the edge of the circle? So that would be measured in inches, feet, centimeters, things like this. However, we can also measure arcs in terms of their measure as opposed to their length. Not how long it is, but how much of a circle it is. For instance, both of these arcs here in green are both 42 degrees. That's their measure. However, they differ in length. Arc DE is obviously longer than arc BC. The circle that BC is a part of would be smaller than the circle that DE is a part of. So they have the same measure, they represent the same proportion, but they are different lengths. So keep that dichotomy in mind, arc measure versus arc length. I'll make that very concrete here. Both of these arcs have the same measure. That measure happens to be 180 degrees. They both represent the same proportion of a circle. Where they differ is their length. It is obviously a longer distance that my finger travels here on the bigger arc than the smaller one. There's more blue over here than there is over there. The physical length is longer in one than the other, but they do have the same measure. Let me illustrate this for us. Here you can see a view of what arc measure means, measured in degrees. And here we have arc length, measured in some sort of length unit. It depends on the problem, inches, feet, centimeters, things like this. You'll notice as well there's a formula here that's going to be quite useful that we're going to use in just a moment. And that moment is now. In a circle with angle FGH being 82 degrees and FG being 7, let's go ahead and label those. FG is 7. That's this length, which you'll notice is a radius. And FGH, this angle here, is vertex is G, so F to G to H would be 82 degrees. Find the length of arc FH. So we're looking for arc length. The measure, even though it doesn't ask, I just want to emphasize this, the measure of arc FH would also be 82 degrees. It's 82 out of the full 360. The angle there and that arc have that relationship. But we don't want the measure, we want the length. So we're going to find how long this actually is. Well, what would be nice to know is the full length all the way around. What is that term called? That's right, it's circumference. So circumference is 2 pi times the radius. And hey, we're given the radius is, in this case, 7. So 2 pi times the radius, 7. And this says the nearest hundredth, so I'm not going to leave pi in my answer. 2 pi times 7 gives me approximately, for the full circumference, 43.98. So that's the full length in green. I only want a portion of it, and the portion that I want is the angle in question. So 82 degrees out of 360 degrees is a part-to-whole ratio. I want that proportion or that fraction of literally the full length. So I'm going to multiply the full length, 43.98, by this fraction to find literally the fractional portion of the arc, or of the circumference, which we call an arc. So 82 over 360 times 43.98. We expect this answer to be a lot less than 43 because not much of the arc is purple here. And indeed, if you do the math here, you end up with an arc length of 10.02. The full thing is 44-ish. The arc is about 10. To illustrate this formula, again, you'll notice 2 pi times the radius, circumference, times the fraction, in their case here, with the angle being shown. Some more key terminology. We have central angle and inscribed angle. Which one do you think is the central angle and which one's the inscribed? Right? The central angle would naturally be angle COB vertex is the center, kind of a no-brainer. And the inscribed or drawn within angle is the angle over here, CAB. So COB, in this case, is the central angle. CAB is the inscribed angle. Now, there's a key idea about central angles that I want us to focus on here. You'll notice in this case here, angle AOB, different terminology, but same basic idea, is a central angle. And you'll notice over here with vertex P, you have an inscribed angle. An inscribed angle, by the way, to give you a precise definition, is an angle whose vertex is on the circle. So you'll notice the vertex of the angle here is on the circle. And what I want you to notice is the relationship between the two angle measurements. It's not always going to be the exact right pair of numbers because of the way rounding works in the software, but you'll notice a pattern. As I make the central angle something, what do you notice about the inscribed angle? You'll notice that it's always half as big, and that's a key idea here. So let me label some things here. Let's call this x degrees. The central angle will be the exact same measurement. If you pause and think about it, my hope is that makes sense to you in terms of if I make this 180 or close to it, then the angle here in between to the center would be a straight line. The central angle and the arc have the exact same measurement, x degrees, x degrees. What we just saw illustrated through that illustration there is that the inscribed angle is always half of that. So in this case, that would be 1/2 x degrees. So inscribed angle, again, vertex on the circle, is half the measure of the captured arc. By captured, I mean imagine for a moment the outstretched arms of this angle stretching outwards from the vertex. And within its arms, in between its fingertips, is the arc, and it is half as big as that. The arc is x degrees in red, the angle is 1/2 x degrees. Let's look at an example. In circle B, with measure of angle ADC being 25, pause, let's illustrate that. ADC, that fellow right there is 25 degrees. Then find the measure of angle ABC. What we just saw is that the inscribed angle is half as big as the arc. Or to put it another way, the arc is twice the inscribed angle. So what that tells us, excuse me, is that this arc right here, captured by the green arms of this angle, is double 25 or 50 degrees. Well, that's nice because the angle being asked about, let me read the question now, find the measure of angle ABC. Well, what do you know? Angle ABC is a central angle, therefore, it is also 50 degrees. Easy. You just have to know that 2-to-1 pattern. Are they always this easy? Not necessarily. Let's take a look at this one here. There's a couple ways we can work this problem that might be beneficial to you. One thing you might realize is that you have a 70-degree angle here, which means that this arc would be double that, or 140. You have a 49-degree angle here, so its arc would be double that. Again, 2-to-1 ratio between inscribed angle and the captured arc. So you'd have 98. Well, what do the purple arc, the orange arc, and the magenta arc all add up to make? Well, it's a full circle, isn't it? So it should be 360. So from 360, I'm going to remove 140, and I'm going to remove 98. So that leaves me with 122 left over for my missing arc measure. Or you might realize that, hey, this is a triangle. All triangles measures their angles add up to 180. So subtract 49 and 70 from 180. So, hey, they may as well give us this to be 61 degrees. And what do you know? Intercepted arc, inscribed angle, 61 times 2 gives us 122. Either way. So I mentioned earlier arcs were important. We've seen arcs quite a bit. Let's talk now about chords. Chords are segments, line segments, whose endpoints are on the circle. So here's a chord, and there's a chord. And when chords cross, you have this interesting pattern that emerges that I wish we had time to prove, but unfortunately we don't today. So I'm just going to tell you what that pattern is. That pattern is over here. This is called the intersecting chord theorem. It's very easy once you know it. It says that the ratio, or the product rather, to be less confusing about it, of this times this, the subdivisions of one chord is equal to the product of the subdivisions of the other chord. A times B equals C times D, or blue times blue equals green times green in this illustration here. Very, very simple. You just have to know it going in. To illustrate, we have two chords. One is sort of vertical, and the other one's sort of slanted downwards. So the slanted downwards one has its subdivisions as x and 4. So let's see here in blue, x times 4, the product of one pair of subdivisions is equal to the product of the other pair of subdivisions. The vertical chord is subdivided into a piece of 5 and a piece of 8. So 5 times 8. Again, just applying this pattern of the intersecting chord theorem. I don't know if you can make that all visible here, but same basic pattern. A times B equals C times D. Same deal here. Well, solve. It's easy. 4 times x is literally 4x. 5 times 8 is 40. Divide both sides by 4. And without breaking a sweat, you have your answer, which is 10. Super simple. Just have to know the formula. Less simple are circles on the coordinate plane. So we haven't really talked much about the coordinate plane recently. We've been sort of in a variety of topics related to volume and surface area, but here we're talking back on the grid. And on a coordinate plane or graph, circles have a very kind of intimidating looking equation, but it's actually the distance formula, or it's the Pythagorean Theorem is another way of looking at it as well. Again, wish we had more time to prove this, but unfortunately at the moment we don't. What I want us to focus on here are the two ingredients needed for the equation of a circle. The equation of a circle has the ingredients including the radius, that's a critical part of a circle, that's how wide you make a compass is 2 parts, and the center, that's where you actually put the needle of the compass down. So when you think about making a physical circle, the radius and the center are fundamental to its creation. And so it is for the equation of a circle. The equation of the circle is this. I'm going to try to color code this a bit. No, not. Okay, that may look exotic to you, but there are not that many important things to know here. Just a few. Really just 3. H and K are numbers that correspond to the center of the circle. Those are the coordinates of the center, which you can see right here in general. R, you can probably guess, stands for the radius. It's the length of the radius. You'll notice this has a very familiar pattern to something we've seen quite often in this class, which is the Pythagorean Theorem. It's something squared plus something else squared equals a third thing squared. My laser pointer is a little laggy here, but you get the idea. Thing squared plus thing squared equals third thing squared. So make sure you know this formula. It's a little exotic, but let's look at an example to close out. What is the equation of this circle? The equation I just wrote is a pattern that we're going to fill in. So here's our pattern. There are 2 things we need to apply this pattern. We need the center and we need the radius. In general, the center is called h comma k, but we know the center of this circle. The center of this circle, if you look carefully here, is given to us at 5 comma negative 2. So that tells me that my center, 5, negative 2, my h is going to be 5, and my k is going to be, my k is going to be negative 2. Again, h and k here are the coordinates of the center, h comma k, 5 comma negative 2 in this case. So 5 is going to go here, and negative 2 is going to go there. We're 2/3 of the way done, folks, because all that remains is the radius. The radius is the distance from the center to the edge. Let's take a look here. The distance, being that the grid here is based on 2's, we have a distance here of 2, 4, 6, 8, and then half, so 9. So the distance here of this segment would be 9 units, right? So the radius is 9. All that remains now is to plug everything in. So our final answer, told you it was easy once you know the formula, x minus y minus equals squared. Okay, let's fill in the gaps. H was 5, k was negative 2, and the radius was 9. To simplify this a little bit, I'm going to write this as the following. Nothing to do there. Minus negative 2, that's right, it's plus 2. And 9 squared, well, that's just 81. And that's it for this video.